Okay, this is the second video now on the conservation of energy, the law of conservation, I should say. So we just got through talking about the fact that energy cannot be destroyed or created, but it can be transferred or transformed. Transferring means just like, hey, I'm going to take this can of gas and I'm going to move it over here. It's still the same amount of energy, it's just been moved basically. But even that takes energy to do that. So energy transformations, now we're going to go through and take a look at a couple examples. For example, this one right here. Some people say, oh, this is wind energy. And it is, but that's not a form of energy. We start to think, what's actually getting transformed to what? You always remember, if anything's moving right now, so you can't see the wind, but you can infer it's actually there because the windmill is moving, then the wind was basically just motion energy or mechanical energy of the wind hitting these wind turbine blades and turning them. So it's actually just transferring energy from the wind to the blades without transforming the energy. It's still just motion energy. And then inside of the actual, I don't know what you call this thing, the dome at the top, there's a generator where these things are turning that magnet to turn the mechanical energy or motion energy into electrical energy. And that electrical energy runs down wires and then it goes out to the grid and goes to your home, say. So in this case, all that to say, this would be motion energy transferring into motion energy, which transforms into electrical energy. And even in your home, maybe it'll be transformed from electrical energy into watching this video right now on your computer. So we're going to look at a couple examples. First example would be when you're putting gas into a car and the car is using that gas, what is the transformation of energy that's happening there? What form to what form? I'll give you a second. Pause the video. Think about it. Okay. Now unpause. The car would be using chemical energy that's stored up in the fuel. All the fuel has chemical energy, and when you ignite it with a spark, that turns into motion energy, mechanical energy. There's a couple different things that are happening too. There's sound energy that comes out of it. There's also thermal energy. But the main idea is to get the chemical energy to turn into mechanical energy. In terms of efficiency, if you remember back to mechanical efficiency, how much energy you're putting in compared to how much energy you're getting out would be your efficiency. If you get a lot of energy out when you put it in, like close to 90%, you would be making a lot of money, because everything's about trying to get it as much energy out as you're putting in. So where does the other energy go besides mechanical? Sound, thermal, you name it. Motion energy of the car itself, if it's not going into doing what it's supposed to be doing, it's not considered to be efficient. Okay, radio. Take a second and think about this one. What form is energy is going into it and what form is going out of it? Okay, if you said electrical energy going into sound, okay, you can use the speakers. If you said chemical energy of batteries in this thing turning into sound, okay as well, or sometimes it's chemical energy going into chemical energy, or electrical energy if this thing's plugged in into chemical energy of the battery itself. Some people might say, hey, it's producing light. You might have electrical energy getting turned into radiant energy that you can see here and here. There's lots of different transformations happening. Okay, this is also an interesting picture. What about this frog here? Would it be electrical to motion, chemical to gravitational potential energy, which is what GPE stands for, or mechanical to gravitational potential energy? And the answer could be multiples here. Really, electrical signals cause chemical reactions that cause motion in your muscles, or in the frog's muscles. You might think of it in total, mechanical energy of this frog leaping into the air, the motion energy, turning into gravitational potential energy because it's going up, and what up goes up must come down eventually. Microwave. Many people think that this would be something to thermal energy, right? You have like some kind of nuclear reaction going on in there, or it's electrical motion turning into motion. Microwaves actually use electrical energy to create light in the form of microwave radiation. It's not light wave that you can see. We'll talk about that a little bit more when we talk about light. And that radiant energy causes, it basically has a little generator for this light over here. It shoots over here. There's a fan that ping, shoots it down through the food, and it causes the food to vibrate. So thermal energy is what it ends up as, but it comes in the form of radiant energy. That might be confusing. That's just because you don't maybe know that microwaves are light energy, radiant energy. What about this one? This one people usually get messed up. I'll just give you a hint. This is a microphone, not a speaker. So electrical to sound would be a speaker, but this is a sound energy turning into electrical. So the vibrations that go into this get turned into an electrical signal, and that electrical energy flows down a cord eventually, or if this is a wireless mic, it would actually be using light to transfer the signal to the receiver, and it's going to get turned into sound in the speaker. So once again, tons of ways to think about these things. If you can accurately explain any one of the many transformations that's going on in any of these things, that's fine. And the last examples we'll do here is the process of photosynthesis. The Earth is not really a closed system, meaning it's not like energy doesn't escape or come into it, because energy does escape it. Light escapes Earth. You can see Earth from space, so there must be light coming out of it, and that light has energy. The atmosphere is a pretty good blanket for us, but some heat does escape. But really, there's lots of energy that comes in the form of radiant energy from the sun. We keep getting more and more of the sun's light. Over time, over millennia, over millions and billions of years, the Earth has received a lot of energy from the sun. So that sunlight comes in. Certain things on Earth have adapted to this. Plants, specifically, take the sunlight's energy, what we call radiant energy, and they use that to stitch together little molecules inside of their chlorophyll and chloroplasts to turn it into sugar. So it takes the radiant energy and stores it up as chemical energy. So radiant energy turning into chemical energy. And if you were to eat a plant, say, you would be turning its chemical energy into motion energy. That's basically the process here. But in that process of photosynthesis is basically taking the sun's light in order to stitch together chemical energy, making different molecules. Okay, a match is a common one that you see on tests. They're not my tests because there's no test for this. It would be chemical energy that's stored up in the tip, turning into thermal energy. Okay, I'm going to skip these. So independent practice. This one, I'm going to have you do this yourself. We're going to go back into our Got It notes at this point. If you can see at the bottom of your notes, there are plenty of places to do review. So you have types of energy review if you want to go back to your notes on types of energy, forms of energy, just matching here, and conservation of energy. I want you to pause the video right now and try to complete as much of these review pieces as possible. Maybe spend 5 to 10 minutes on that, maybe 10 minutes really. And then as soon as you're done, unpause this video and I'm going to review each one. Okay, I'm going to imagine that you just completed the guided notes here. If you didn't, you're not fooling me, it's your practice, okay? So I gave you instructions to determine the best match between the basic types of energy and descriptions provided. Put the correct letter in the blank, so the blank's here, right? So this is just labeling the types of potential energy or kinetic energy. A skier at the top of a mountain has potential energy from gravitational potential energy. They're up high, they have the potential to get energy to go down the hill. That's why skiing is fun. Gasoline in a storage tank, unless it's blowing up, it's in a storage tank, right? It's potential. There's a lot of potential in that gasoline to have matter being changed. So this would be potential energy. A race car traveling at its maximum speed is energy in motion, right? If it can't go any faster than that, then it must be no potential energy at all, just it's completely kinetic energy, KE. Water flowing from a waterfall before it hits the pond below. Well, this is kind of tricky. If it's flowing from a waterfall before it hits the pond below, then it's probably a mixture of both, right? It probably has some kinetic energy still because it's moving, but it's still high up, and the idea would be the further down it goes, the less potential it still has, but it's all getting transformed into kinetic energy. A spring with a pin in a pinball machine before it's released would be potential energy, stored up as a conditional potential energy in the molecules themselves. Burning a match would be probably kinetic energy if you think about that. It's getting turned from potential energy in the chemical energy in the match tip to thermal energy, which is hot. A running refrigerator motor would be kinetic energy. This is a motor, this is something that's moving, and there's stuff moving going into it. Electrical energy is moving energy as well. Okay, the review is continued on the next page here. So forms of energy now. And I recommend if you miss these things or you just don't understand them, maybe go back to the lesson or the helpful video on kinetic energy and potential energy. Okay, forms of energy. Match the energy forms to the description below. A few questions may have more than one answer. We'll just try and do one for now. So here we have motion, electrical, thermal, radiant, chemical, nuclear, and sound. Falling rocks from the top of a mountain would be motion. There's no really better way of explaining it by any of these other things, so we're just going to say, yep, it's in motion, motion energy, also known as mechanical energy. The release of energy from the sun, that is, sometimes people say solar energy or light energy. The word that we're trying to use here is radiant energy because it shoots out as a ray. That can include anything that comes in the form of light, which can be microwaves, radio waves, visible light, ultraviolet, X-rays, gamma rays, you got it. Energy released from food after it's eaten would be chemical energy. The energy inside the food, I guess you would say, is chemical energy. Batteries also have chemical energy. Basically, there's chemical reactions that go on there. There's a whole bunch of different types of batteries, but most of them work that same way. You have like a nickel cadmium. Those two elements inside of those batteries store up charges, and basically as soon as you start to put a demand on them, they will rework themselves and deplete themselves. Some of those are rechargeable, so you can actually put energy into it and they reconstruct. It's a very simple way of thinking about it. The energy that runs a refrigerator would be electrical energy. These are free electrons moving into the refrigerator's motor that causes the motor to run, or the compressor. Nuclear fission reactors would obviously be nuclear energy. That's the nucleus of an atom. The rumble of thunder from a storm would be sound energy, G. Rubbing your hands together would create thermal energy, but it comes from motion energy, if you want to think about it like that, maybe A or C. And then gasoline would be chemical energy. Food before it's eaten. Oh, okay, so E. Actually, food, energy released from food after it's eaten. Hey, that could be sound for all you know if you're farting because of all the energy you got from that stuff, but mostly you think about motion. That'll allow you to actually move. And lightning could be a mix of sound. I'm sorry, yeah, lightning is not thunder. It would be basically radiant and thermal energy. If you need to stop it here to just make sure of your answers and compare them, go ahead and do that. Once again, if you're having a hard time with that, I would suggest that you go back to refresh yourself on forms of energy. Finally, this one I'll just talk through. A battery that runs a moving toy would initially start with chemical energy and go into motion energy. A solar panel that's on the roof of a house takes radiant energy from the sun and turns it into electrical energy. A person lifting a chair uses motion energy, and since they're lifting it, it means that it's getting gravitational potential energy. It's getting stored up as they lift it higher and higher. A nuclear power plant takes nuclear potential energy and turns it into thermal energy, which is what causes turbines, and eventually you get electricity out of that. Toaster would take electrical energy and turn it into thermal energy, and a little bit of light. You think about a toaster as a terrible light bulb. Church bell would take motion and turn it into sound. Gasoline would take chemical energy and turn it into motion energy, thermal energy, and sound. A light bulb would take electrical energy and turn it into thermal energy and light, or radiant energy, and photosynthesis, finally, radiant energy into chemical energy. Okay, I hope you like these videos for the week. That's the last video of the week. Do your best, and remember, do your PHET simulation. See ya!